Hello friends, welcome back to Domain Analytics program we conducted by 360DigiTMG, and we are looking into insurance analytics today. Okay, so we have started with day one. Okay, this is a 1 week program. Okay, in this program, in the day one, we have started with applications. Okay, of insurance analytics. So in the same way, so we have seen if we have data from insurance industry. Okay, so what we have to do? So we have to collect data, we have to analyze data, and these insights that we get, that will be applied. Okay, that will be used for some applications. So the various applications we have seen, such as designing a new product. Right? We have seen designing a new product. In the same way, we have seen the targeted marketing. Okay, based on the analysis, we target a specific segment and we try to market the product there. In the same way, to predict fraud. Okay, that is going on to predict the fraud. Okay, that is going on in insurance industry. Okay, claims. Okay, sometimes you can say that the claims are fraud. Okay, so beforehand only, based on the data what we have, we can analyze and recognize, okay, which claim could be a, okay, which policy, okay, which policy order could be a fraud. Okay, it could apply for a fraud. Okay, these details you can get in the same way in the process of insurance claims also we are using data science. These are different applications that we have. So after that, we have seen the EDA, right? We have started with the CRISP ML process, right? CRISP ML process, CRISP MLQ. Okay, we have seen that we have business understanding and data understanding. Okay, in the same way, data pre-processing. We have the second phase, that is data pre-processing. And the third process that we have is machine learning. Okay, data mining and machine learning. We can say, okay, this is the process where we select our model. So this model, okay, has to be evaluated. Okay, this model has to be evaluated for the performance. Okay, if my model is working or bad. Okay, and this to be applied. Okay, this to be deployed. This model that we have built, that should be deployed in a mobile or web application. So the monitoring, okay, monitoring and maintenance is very important step where we will be monitoring the deployment process. Okay, if there is any changes, we again make changes there. So that comes under quality assurance. Okay, these are 6 different phases that we have. Then we have seen the EDA part. In data preparation, we have seen EDA and data pre-processing. So we have seen EDA and data pre-processing. So in the next step, okay, we have seen what are the different steps we have. So how we have to clean, what will be noisy data. Okay, all these details we have covered in data pre-processing. Okay, then we started with our data mining. So in case of data mining, we have 2 different learnings. One is unsupervised learning and the second is supervised learning. In case of unsupervised learning, we'll be having unlabeled data. Okay, we do not have label for this data. In case of supervised learning, we'll be having label. Okay, that is nothing but output. Okay, we'll be having input values and we'll be having output. Here we'll be having only input values. Okay, so in this we have seen K-means clustering, where we have seen the data. Okay, where we have seen the data that is related to market segmentation. Okay, we have seen data that is related to market segmentation, and we have used credit card details of SBI customers. And based on the process, based on the analysis, okay, we have divided the data into three different segments, right? That we have seen in K-means. Okay. The same way we have covered the KNN also. It's a supervised model. Okay, it's a supervised model. Okay. Okay, it's a supervised model. Because of supervised model, okay, we have seen KNN and we have completed the data science. Okay, sorry. Right. So today we are going to look into regression. Okay, so before going there, okay, when it comes to supervised models, okay, when it comes to supervised models, we have two types. Okay, so one is classification models. Okay, we have classification models and we have regression models. Okay, in case of classification models, we'll be having the output. Okay, the output that we have, that will be, okay, categorical. Okay, we'll be having that is a discrete value. I'll be having a discrete value here. Okay, and that is categorical, like yes, no, spam, ham, right? So in the same way, when it comes to regression, the output value will be continuous. Okay, we'll be having numbers here. Okay. Based on this data, we have to predict. Based on this data, we have to predict. So we have seen KNN. Okay, we have seen KNN, that is a classification model. Okay, that works on distance. Okay, that works on distance measure here. In the same way, when it comes to decision tree, that works on probability. Okay, that works on the basis of probability. Okay, so to be precise, it works on, okay, condition probability. When it comes to we have one more. Okay, sorry. We have naive Bayes. Okay, naive Bayes that works on the principle of probability, and in case of decision tree, okay, in case of decision tree, it works on classification rules. Okay, we have seen what is decision tree, and we have taken the data and we have gone through. So in the same way, we have regression. Okay, regression problems. Okay, so in regression problems, we have two types: simple linear regression and multiple linear regression. So in case of simple linear regression, okay, it depends on the data. Okay, what data we have. Okay, the first thing we consider is, okay, see the output. Okay, y is output value. Okay, and in case of one more thing that we consider is the input values. Okay, if I have only one input value, okay, one independent value, okay, one independent variable and one independent, okay, one dependent variable, okay, that is output, then I will be using simple linear regression here. Okay, if I have multiple independent variables, okay, and I will be having a dependent variable here, I will be using multilinear regression. So let us see what a simple linear regression is. So today's topic is simple linear regression, and we'll be looking into regression analysis, linear model, correlation analysis, equation of straight line, simple linear regression, and a business use case. So when it comes to regression, okay, what is regression analysis? Okay, when we say regression analysis, regression is used to study the relationship between two different variables. Okay, so when we are, okay, we have two different variables. I'll be looking into relationship between two different variables here. Okay, we can use simple regression if both dependent and independent variable are numerical values. Okay, and in simple case, I'll be having only x and y values, and these are numerical values. Okay, if dependent variable is numerical but the independent variable is categorical, okay, so we will be converting this value, okay, we'll be converting this value into dummy variable. Okay, okay, the following, okay, here we have few situations, okay, that where we can, okay, where we can use the regression principle. Okay, testing if IQ affects, okay, if IQ affects income. Okay. IQ is the independent variable and income is the dependent variable. Right? I have two different values. Okay, here simple linear regression. We are speaking about simple linear regression. So usually IQ will be is a numerical value. Okay, in the same way we have income. Income is also a numerical value. Okay, so testing if hours of work affects hours of sleep. Right? There is some correlation, right? We'll be looking at correlation. Okay. Dependent variable is hours of sleep and the hours of work is the dependent, okay, independent variable. Okay. So testing if the number of cigarettes smoked affects blood pressure. Right. So if there is any relation between cigarette smoking and blood pressure, so we are trying to find the relationship between two different variables. Okay. So that is regression. So we have the numerical data here. So we are trying to find the relationship between these two variables, and then we'll be trying to predict. So it is very important to understand this scatter plot here. Okay. So in this scatter plot, as we have discussed earlier, okay, the details such as income. Okay, income is in my y-axis and IQ is in my x-axis. Okay, so what it is showing here, okay, this shows that if my income increases, okay, and my outcome, okay, my IQ increases, my income increases, right? It's a positive correlation what I'm seeing here. So this is a linear relationship. I can see a linear relationship here. Okay. So, and this is particularly we call it as a positive relation. Okay. When both values are increasing. In the same way, if my income, okay, if my income is increasing, okay, if my income is decreasing, okay, and my IQ is increasing, okay, in this case, I'll be having values in this way. Okay. It will be coming down. Okay, it's a negative correlation. We say that it is a negative correlation, and if it is following a straight line, okay, all the values are following in this affinity. Okay, so then we can call it as a positive and strong correlation. Okay, all the values will be having here. Okay, in the same way, if the values are following in this way, okay, in this way, okay, in this line, we can say that it is negative correlation. Okay, so there are few chances. Okay, there are few chances. We have values in this way also. Okay, here we can see that we have body fat percentage and chance of heart failure. Okay, here I can see that the values are not following the right. These are called curvilinear. Okay, curvilinear. We have a curve here, right? These are curvilinear, and it is a not non-linear relationship. What we have. Okay, it's not. No, it's a non-linear. So this is what we have here. Okay. So we have as per the discussion what we have seen earlier. Okay. So we can notice that this is a strong positive correlation. Right. All the values are going in the line. Okay. The same way here we can say that there are few deviations here. You can say few deviations here. Again, it is coming like this, right? So this is moderate positive correlation, and in this case, okay, these are all scattered like this. Okay, I can say that there is no correlation between these two values. Okay, when I'm saying correlation means it is relationship between two different variables. Okay, we are speaking about two different variables here. So it is, see, we can see that the values are coming like this. Okay, values are coming like this. Okay, that means so the y value is decreasing and x value is increasing. Okay, so in this way, okay, this is a strong negative correlation and moderate negative, and this is the curvilinear relationship what we are saying. Okay, up to this level it is coming down and suddenly it is taking a linear position here. Okay, so we use, okay, scatter diagrams provide or plots provides a graphical representation, okay, of two continuous variables. Okay, we must be careful that correlation does not guarantee causation. Okay, that is very important because if I have an example like okay, there is a ice cream, okay, ice cream factory, okay, ice cream factory, okay. Here I am looking into sales, okay, the sales are increasing, okay, and here in this case I am seeing that there are a lot of sunstroke cases. Okay, so in this case, if I see the data, I can say that my X value is increasing and my Y value is increasing. Obviously, if I mark this, okay, if I plot this, I'm getting a strong correlation, positive strong correlation. But is there any correlation between these two? No, right? So it is very important that we must be careful that correlation does not guarantee causation. It's not, it doesn't state that there is a correlation. Okay, there okay, the plot shows that these values are in a linear format, but there is no causation here, right? In case of negative correlation, X will be increasing and Y will be decreasing. In case of positive correlation, both X values and Y values will be increasing. Okay, but we have to look into causation also. That is also very important. So what do we have in linear model? Okay, so when we are saying linear model, the basic equation that we know is y is equal to mx plus c. Okay, so m is slope, okay, the rate of change. We are speaking about the rate of change here, and c is the coefficient what we have. So if we are taking a line, okay, if we are taking a plot here, and if I am plotting a line here, okay, if I am plotting a line here, I have some data. Okay, as we have seen earlier, I will be having some data. Okay, this is my actual data what I have. And if I want to predict, okay, so this I am taking the help of linear regression here. Okay, I will be checking the linearity. Okay, I will be using the equation y is equal to mx plus c. Okay, where in this case I'll be having coefficient. Okay, this point where my y axis is getting intercepted here, that is y intercept. Okay, y intercept is beta naught. Okay, in the same way the rate of change, okay, if for every 1 unit of my x, okay, how much is my y is changing. Okay, that I will be getting by, okay, the slope value. Okay, the rate of change, how much it is changing, that is nothing but that is beta 1. Okay, so I am going to replace these values. Okay, so y is equal to, okay, beta naught plus beta 1x. Okay, this is the same equation what we have here. Okay, if I am trying to find difference. Okay, if I want to find the difference between the actual value and the difference between the predicted value. Okay, this is the predicted value. Okay, so the distance between these two will be my error value. That is my error function. Okay, this is my straight line equation. That is, this is my prediction equation. Okay, and this is my prediction line. Okay, this is my prediction line. Okay, so y is the dependent variable. Okay, for example, dependent variable is income. Okay, the output is income here. Okay, for example, x is the independent variable. Okay, that is nothing but iq. Okay, for example, a is an intercept, right? A is an intercept here. Here in this equation, A is an intercept and B is the coefficient of here. Okay, E is the error. Okay, E is an error term for each observation since there is additional variation not explained by income. Right, there is some variation that has been not explained by the this value. Okay, the x value. Okay, whatever the x value is. Okay, it's not explained. Okay. So the errors we are normally distributed. Okay, that we have to understand that the errors. Okay, the errors what we are taking, they are normally distributed. The line what we are taking here, it is a straight line equation. Okay, it is normally distributed. Okay, this can be tested by plotting a histogram of the residuals of the regression and checking that they all have a bell shape. Okay, by plotting. Okay, if I want to check that, okay, if my errors are normally distributed or not, I can use the help of histogram and I can check that. That I can. So this is nothing but the linear model. Okay, in case of linear model, we assume that my values will be falling in straight line. If my values are falling in straight line, what will be the result? So in this way, okay. So we need to understand the relation between the independent variable and dependent variable. Okay, based on the if there is no correlation, there will not be, we cannot find any relation. Okay, we cannot predict anything. Okay, there we assume that there will be some correlation in the data. Then only we can do some prediction. So correlation analysis measures the degree of linear relation between two variables. Okay, so the correlation coefficient. Okay, if the range of coefficient is -1 to +1. Okay, if we try to quantify the value. Okay, what is the, okay, if I'm saying positive correlation, if I'm saying negative correlation, if I want to quantify that in value, okay, so it will be between -1 and +1. Okay, so if I am saying perfect positive correlation, the value will be +1. Okay, perfect negative correlation, value will be 1. And if I am saying no correlation, that will be 0. Okay, the formula that we have here is that is related. Okay, and it is represented by small r. Okay, coefficient is represented by small r. So this value is very important to us. Okay, if there is any relation only, we can do our regression. So ordinary square, okay, ordinary least square. What are we trying to do? We are trying to find the least error values, right? So now if I say my intercept is here and my values are here, okay, based on this I am trying to calculate what do I have here. Okay, the mean value of y when x equals to x naught. X naught is nothing but the mean value. Okay, the mean value what I have here. In the same way, an observed value of x, okay, an observed value of x when x equals to x naught. X naught is nothing but the mean value what I have. So I will be trying to find the error term that is least. Okay, that is least value. That has the least value. Okay, this intercept may be here. Okay, this intercept may change here. Okay, based on that, the line will be drawn. Okay, so I will be drawing a line in such a way that I will be having least error. Okay, so we have to fit the value in this way. Okay, y hat is the predicted value. Okay, fitting a straight line by least squares. Okay, b naught plus beta x. Okay, so we know the straight line equation already. Okay, y equal to beta naught plus beta 1x. When we are considering the least square error, okay, y hat is equal to beta hat 0. Okay, okay, beta naught hat and beta hat x. Okay, these are the values. So ordinary least square regression is a common technique for estimating coefficients. Okay, estimating coefficients of linear regression. Okay, for estimating coefficients of for estimating these values. Okay, beta naught and beta 1. If I want to estimate these values, okay, I will be using ordinary least square errors, OLS. Okay, which describe the relationship between one or more independent quantitative variables. Okay, when I'm saying one or more independent variables, it is about simple and multiple linear regression. Okay, in simple linear regression, I'll be having only one independent variable. In case of multiple linear regression, I'll be having multiple variables. So we have to determine, okay, we have to determine the variance between the values. Okay, I have the x and y. Okay, what is the variance? Okay, what is the variance between the data? Okay, that is important. Okay, variance between the x value and y value. Okay, that is also very important to determine the if I want to predict anything. Okay, if I want to predict anything, that is very important. Okay, so we are going to calculate the R squared value. Okay, R squared value. So what is R square value? R square also known as coefficient of determination. Okay, which represents the percent variation in output. Okay, what is the variation in output when, okay, when my input variable or variables or percentage of responsible, okay, responsible variable variation, that is explained by its relationship with one or more predictor variables. Okay, it means if there is any change, okay, if there is any change in y, okay, is there any change in x? Okay, that we not forget, that variation we have to calculate. Okay, higher the R square, the better the model fits your data. Okay, that's the phenomenon that we have to remember. In the same way, R square is always between 0 and 100%. And in case the R square is 0.65 to 0.8, we can take it as a moderate correlation. And if it is more than 0.8, it is strong. It depends on the domain. Sometimes we take more R square value to determine the data. So mathematically, we have to calculate the SSR, okay, the residual, the sum of square of residual, okay, the sum of square of errors, and total sum of squares. Okay, we have to calculate this and some, okay, SSR by SST, that gives me the R value. Okay, the R value will always be between 0 and 1. So the prediction and confidence interval are types of confidence interval used for prediction. Okay, as we are dealing with continuous data. Okay, we are working on continuous data. Okay, it is not possible to get the probability for one event. Okay, okay, if I want to calculate, it will be zero. Okay, so we have opted for confidence interval. Okay, okay, we will be taking the data, the probability distribution. Okay, as, okay, we'll be taking the probability distribution as standard probability distribution, and we'll be considering the middle value. Okay, it will be as zero. Okay, mu is zero, and the standard deviation is one. Okay, we'll be converting the data in this way, and we know our, okay, we know the data. Okay, here I will be having 99% data, and the rest will be alpha values. Okay, where alpha is nothing but significant confidence, significant data alpha. Okay, 1 minus alpha, 1 minus alpha will give me, okay, will give me 95%. Okay, so my estimate will be falling here. Okay, that's the phenomena what we have. And the rest of the data, okay, rest of the alpha value, okay, the alpha value is that it shouldn't be zero. Okay, the value shouldn't be zero. Okay, if the value shouldn't be zero, if it is not zero, okay, ultimately, definitely it will be some value. Okay, there will be some value. That's the hypothesis that we take care. Okay, we consider the null hypothesis, where null hypothesis we see that it is the value is not zero. Okay, we take it as value is not zero, and if the value is not zero in alternate hypothesis, we say that there should be some other value. Okay, so we consider confidence interval, and based on that, okay, based on that, we will be getting the straight line. Okay, we'll be taking the confidence interval, and so that my estimate will be coming here. Okay, how do I calculate my confidence interval here? CA is equal to point estimate. Okay, point estimate is nothing but x bar. Okay, plus or minus. Okay, plus or minus. We'll be taking margin of error here. That is my confidence interval. Okay, these are we calculate the confidence interval, and we will be taking the value as the data is in continuous format. So when it comes to simple linear, we know that we'll be having the x and y values. Okay. So when it comes to y, it is a continuous data. Okay. When it comes to x, it is a single and continuous data. That is simple linear regression. Okay. In the same way, if y is continuous and it is single and discrete, what we have to do? We have to convert the data into dummy variable. And this is, and we get simple linear regression. So error variable, okay, we have to discuss about error variable, okay, that is okay. So the critical error, okay, the error is a critical part of regression model, okay, and four requirements, okay, four requirements involving the distribution of E must be satisfied. That is the error, okay, to recognize the error. The probability distribution of E is normal, okay, the probability distribution of E is normal. The mean of E, okay, the mean of E zero is okay, that should be zero equal to zero. The standard deviation of error is okay for all values should be x, okay, and the set of errors associated with different values of y are all independent. Okay, these are few things that should be taken care of. Okay, so we are looking into a use case here. Okay. Before that, okay, if you have okay, so we are looking into use case. Okay, there we have to predict charges. Okay, these are insurance claim charges. What we are looking into is insurance claim charges, and we have data. Okay, age. Okay, sex, BMI, children, and smoker, and region. Okay, this is the data that we have here. So what we are trying to do is we are trying to calculate the claim. Okay, we are say this is a continuous value, right? We have a continuous value, but we have multiple values. Okay, how we are going to do a simple linear regression? Okay, the condition we know we should be having one. Okay, we should be having only one value here. Okay, so let us see how we are going to do the simple linear regression. So we are trying to we have describe function here. Okay, it's a descriptive analysis. Okay, I am trying to look into this data. Okay, find some description of my data. Okay, the total count of my data is 1338 1338 values I have here. And in case when I'm taking mean, okay, mean value of age, I have the approximately 40 is my mean. Average age of the person is 40, and minimum age is 18, and maximum age I can say it is 64. Okay, we have minimum age and maximum age here. And when it comes to BMI, okay, body mass index, okay, we'll be calling it as body mass index. That is very important. That is very important when we look into different regular checkups. Okay, so the BMI, okay, the mean is 30. Okay, BMI I can see here it is 30, and minimum value that I can see here is 50, and maximum is 53. And if there are any children, the person who has taken the policy, I am looking into details such as if there are children or not. Okay. For example, in mean, okay, on an average there is one child, okay, in the total data, and I can notice that minimum, okay, there are no children for few customers, and there are the maximum is 5 in number. These data that we have is the numerical data. Okay, this is the only numerical data. In case of here I am seeing like we have categorical data also, right? We have the gender, okay? We have if the person is smoking or not, okay? And the region, okay? We have region, okay? That I want to see that I want to see the description. So the total count, we have 1338 records, and when I am taking gender, I have two values in gender, two categories in gender. In case of smoker, I have two categories. In case of region, I have four categories. Okay, and the total, okay, male. Okay, when we take male, okay, I'm taking one value, and I just want to check the frequency. So the male are 676. So the remaining will be female values, and non-smoker is 1064. Okay, we can see that there are more. The percentage is more when it comes to non-smokers. Okay, and we have approximately like 300. Okay, 300 values that we have. They are smoker. So are there any outliers in the data? Okay, we are seeing in region. Okay, we are doing some univariate analysis. Okay, and here we are seeing the outliers, and we are comparing this with claim amount. Okay, when comparing with claim amount and region. Okay, we are trying to find if there are any outliers. Okay, I can see there are some outliers in southwest, southeast, and northwest and northeast. Okay, there are less number of outliers in southeast, but remaining all, I can see that there are outliers. Okay. The maximum range, okay, we can see here in southeast region, the maximum range that went to 20K. Okay, the maximum minimum value. And here we can see in southeast, the maximum value that I can see is 40K. Okay, that is the claim amount. And on an average, the least I can see here is approximately the maximum value I can see. It's like between 20 to 30K. That is in southeast. So distribution of insurance cost by smoking status. What if, if the person is smoking, okay, maybe the assumption is like there may be many health issues and all. Okay, so we are looking into this data. So to ensure that what is happening with smokers and non-smokers. Okay, who is claiming more? Okay, something like that. We can see clearly that non-smokers, okay, non-smokers, that data we can see here. Okay, this is where we can see the non-smoker data, and there is a less claim. Okay, there's less claims were done in case of non-smokers. Only up to 10K I can see there are only few cases. Okay, there are only few cases they are applied here, but here in case of smokers I can see the huge difference here, right? There are claims up to 60K also, right? So there is some correlation between the smoking, and I can say that there is some correlation between smoking and these values and claim. So when it comes to claim amount and smoking status and age, okay, now we are taking three different values here. Okay, so multivariate analysis. I'm going to do the multivariate analysis where I have claim amount, age, and if the person smokes or not. Okay, so here I can see clearly. Okay, from age 18 to 29. From age 18 to 29, uh, I have both. Okay, see, in all different ages, I can find smokers. Okay, the people who are smoking, and in all different ages, the people who are smoking are applying for the claims. Okay, more claims are being applied by this people. Okay, that we can say clearly. Non-smokers, yes, the number is less. Yes, though it is increasing based on the age. Okay, that also we can observe. The trend is increasing based on the age, but based on the age, we know maybe there may be more health issues, and based on these reasons, they might be applying. Right? They might be applying for the claims and all. Because health insurances will cover the hospitalized if they are hospitalized or anything, it will cover all the benefits. So based on these analysis, maybe. So what are the different fields that have the correlation? Okay, so we can see charges and smoking. Okay, if the person is smoker and charges, we can see a clean correlation here because the value we have given from 0 to 8. Okay, the color variation that shows me the difference, right? So here I can see 0.79. Okay, we are trying to find the correlation between these and charges. Yes, I can say that there is correlation. The same way, I can find some correlation between charges and what is the value here? Age. As age increases, the charges are increasing. These both things we have seen. Okay, in the same way, we have BMI. Okay, this also can be considered. BMI and charges. Because as the age increases, the health the index changes. Okay, so all these changes are coming. So these are correlated. So we have tried to build the model, okay, based on the regression, okay. So we can see here clearly, okay, number of. So here what we have done, we have used the PCA method. Okay, we have used the PCA method, and we have converted the data. Okay, we have used a PCA method and we have converted the data, and based on that data, the values I can see. Let us see the same in the program. I'm opening the Python program, the algorithm in Google Colab here. Okay, we are trying to analyze. Okay, we are trying to predict the insurance prices. Okay, based on the different conditions here. Okay, I have imported all the different modules that are required here. I have uploaded the data, and here this is my data. Okay, this is my data. What I have. Okay, so we have seen the data here. Let me take this into Jupyter. Yeah. So this is the data what we have. Okay, this is the description what we have. Okay, we have the values. Okay, we have the categorical values that we have seen. Okay, what are the different categorical values we have? Okay, we have seen the male and female. Okay, we have tried to find how many male values we have. Okay, what is the claim value? Okay, that analysis we have done here. Okay, so each area, okay, how many policy holders we have, and what is the claim amount? Okay, that also we have tried to find here. Okay, so in the same way we have worked on the. Okay, so we have converted the data. Okay, we have converted the data. We have used the PCA analysis. Okay, using principal component analysis. Okay, the data what we have here. Okay, the data what we have here, we have converted the data into single column. Okay, we have only two columns. Okay, we have taken one column because we are doing simple linear regression, we have taken one column, okay, and the second column is my output column, x and y values, and based on that, we have completed the analysis. Okay, these are the results what we have got. Okay, so for the R square value we can see here 17.9. Okay, when it comes to southwest, and in case of R square value 90. Okay, in case of southeast, okay, and R square value is 74, and R square value is 63 in northeast. So we can see the best relation. Okay, best relation that we can find here is 90. Okay, based on this we can do our prediction. Okay, so the average, okay, by taking linear regression, the average RMSC that we have got here. Okay, so the linear regression performs the best predicting, okay, insurance cost, okay, in the southeast region. In case of southeast region, we are getting the best result with adjusted R square, that is 89.3%. And an RMSC, okay, we can see the RMSC is about 4,700. And this indicates that our model can explain about 89% of the variation in insurance cost and leads to test prediction that are within approximately 4,700. Okay, so this is how you predict. Okay, each model uses 7 principal components. Okay, except the northwest region. This is what we have got here. And the R square that we have got is 74.5. Okay, so that is good. Okay. Based on this, we have got the linear regression here. We can see the values. Okay, how the original values, and we have got the right. So here we have got the highest value here. Okay, 89.3, and RMSE is 4,700. Okay, the least RMSE that we got in southeast. Okay. So what we have seen today, we have seen the simple linear regression. Okay, the linear regression. Okay, we have seen what is the correlation we have. Okay, what is the scatter plot we have, and what are the different correlation values we have. Okay, the strong positive correlation we have seen, the moderate positive correlation we have seen. Okay, and we have negative correlation also. Okay, we are trying to find the relation between them. Then we have seen what is correlation analysis. Okay, what is correlation analysis we have here. Okay, in the same way we have ordinary least square. Okay, we are trying to find the least error. Okay, we are trying to find the least error. Based on that least error, we are going to find the values. Okay, so we will be trying to find the r square value, the variation between x and y. Okay, how these values are changing. And we have seen the simple linear regression. Okay, so we'll be having y is equal to, okay, it is a continuous value, and x is equal to single and continuous value. If it is discrete, we are going to convert that into dummy variable. We have simple linear regression. Okay, so we have seen the error factor, and then we have seen the data. Okay, in the same way, the same data if we take, and if we want to do the multilinear also, we can perform. Okay, will not be converting these values into we have what we have done here in this process. In the current process, we have converted this data. We have converted this data into something like principal. Okay, PCA. Okay, we have done principal component analysis here. We have converted that into one value. Okay, then we have taken this value and this value, and we have conducted the simple linear regression. If I don't want to do this, I can do multilinear also. Okay, in case of multilinear, we'll be having different values. Okay, different input values, and we'll be having it like we'll be finding the y hat there. So this is the difference between the simple linear and multilinear. Okay. There we'll be looking into collinearity factor also. If there is any collinearity factor in between these two. Okay. If there is any collinearity factor, that will be removed. Okay. So all these values will be converted into numerical values. Okay. Numerical values, and then we'll be working on. So in insurance industry, we are using simple linear regression because we have a lot of numerical data. Okay, most of the data that we have, that is numerical data. It could be charges. It could be charges. It could be fraud analysis. Okay, it could be about claims. Okay, what claims we have to take. All these different data. We'll be having a lot of continuous data, a lot of numerical data, and in most of the cases, we are going to use the linear regression model. Okay, in the same way, if I want to do, if I want to do the analysis, if I want to do the analysis where my output value is, my y is discrete. Okay, usually we use our classification models, but also we can do if I have discrete value, I can do regression here. Okay, this is known as logistic regression. Okay, so it depends on the data, what data you are using at all. Okay, it depends on the data. And in logistic regression also we have simple logistic regression and multiple logistic regression. Okay. These are the different values that we have in regression. So we have seen applications. Okay, applications of data science, okay, or data analytics in insurance industry. Yeah. So in the same way, on the next day, we have seen the CRISP ML methodology. CRISP ML methodology, and how we are going to apply the CRISP ML methodology in the insurance industry. We have seen an example there. In the same way, we have on the next day, we have gone through EDA. Okay, EDA and data pre-processing. Right? We have seen some examples there and what are the different techniques we have. And we have seen, okay, on the next day, we have started with data mining. Okay, data mining. And in data mining, we have seen the unsupervised learning model. Unsupervised learning model, that is K-means clustering. Okay. In K-means clustering, we have seen a use case, business use case that is related to insurance analysis. And we had a session, okay, and then on the next day we had a session on supervised learning, right? In case of supervised learning, we have seen KNN. Then again we had a supervised learning, okay, we have seen, okay, decision tree, right? So usually these are classification models. In the same way, today we have seen, okay, we have seen a supervised model, that is simple linear regression. Okay, simple linear regression. Okay, where it is a regression model. Okay, so the output will be different. Okay, here the output will be discrete. Okay, here the output will be continuous. So tomorrow we'll be looking into another supervised learning model, that is ANN. Okay, neural networks. Okay, yeah. Thank you, friends. Thank you for the day. Let us meet tomorrow with a new topic, and we'll be seeing a use case along with the supervised learning method, that is ANN. Okay, neural networks. Yeah. Thank you. Thank you for the day. Have a great day.